I'm with the Boeing Company, and I am
This meeting is being recorded.
And I am chair of the ELISA Aerospace Working Group. As you probably just heard, this meeting is being recorded. If you're not okay with that, please log out. I want to let you know about the ELISA group, working group first before we get to our speaker. The Aerospace Working Group is the newest working group within ELISA, focused obviously on the domain of aerospace. The presentation you'll be hearing momentarily is focused on any area of safety criticality and the Xen hypervisor, but the aerospace group was particularly interested in hearing more from Stefano. If you are interested in joining the conversation about aerospace or any of the other working groups, I will paste in, if you're not already aware, the link to ELISA. Oh, and I see Min already posted as well. Very good. So then let me turn to introducing our speaker. I first became aware of Stefano over a decade ago. I was at a small company that was looking at options for hypervisors, and we were particularly interested in being able to support multiple architectures, not just x86, but also ARM. And it turned out Stefano was leading some of the early development. In fact, I went this morning and looked back, and I'm going to just post this link. If you search for Stefano, Xen, and ARM, you can see he has been a prolific contributor. And if you follow this link, you can see this goes back over a decade to when he was at Citrix and was first submitting the initial submissions for the port to ARM. He has continued his career at Citrix and then went to Xilinx, which, as you probably know, is now part of AMD. So he is a fellow at AMD, and you can see on the slide here, he is also a contributor under the Linux Foundation, not only to the Xen hypervisor, but also to the Linux kernel. Stefano, we're so glad that you are able to take time to share some of your expertise and wisdom about Xen and safety. So we look forward to hearing your presentation. Thank you.
Thank you for the great intro, Steve. All right, I'll start, and if you have any question, you can interact me, but also I'm going to make sure to leave time at the end. See if I can. Right, so we all know, I think we are all here because we care about safety. What is safety? So when human lives are at risk, typically the quality of the software is required to be of very high standard. That is because the software could impact human lives, and not only needs to be very high quality, but we need to be able to prove that is high quality. And there are a number of safety certifications that are different per industry that are used to make sure to certify that the software is high quality, and some of them are listed here on the slide. Embedded hypervisor, how do they help in with this and in general? Like, we are used to, many people, I mean, come from a more non-embedded background where hypervisor are used in the data center, or maybe used on your laptop when you want to run an application of a different OS. What are hypervisor in embedded? I mean, at the core, the technology is similar, but the configuration and the deployment, the use case is very different. So in embedded, hypervisors are used to run mixed criticality workload. And when I say mixed criticality, I mean you have something critical and something not critical. Typically, something critical is small and real time. Something non-critical is larger, maybe based on a regular Linux distribution of some sort, connecting to the cloud, sending back data. So what the saying, don't put all your eggs in one basket, because if something goes wrong, then everything goes wrong, right? That's where hypervisor help you, because they gives you many baskets. They give you as many baskets as you need, right? They give you one for your critical environment and maybe one for the non-critical and more. So real time and isolation are really the key feature here. And when we talk about safety, the critical environment is a safety environment, and the non-critical is typically the non-safety environment. Okay, let's talk a bit more about Xen. So Xen is an open source project under the Linux Foundation. It's a truly community project. As you can see, the chart on the right, this is updated to the latest release that was earlier this year. AMD, the third contributor. And I mean, as you can see, there is not one player that dominates the community. So it's a very diverse and multi-vendor community. This is very important because when there is one company dominating a project, whether it's open source or not open source, and you probably all see it in your own company environments, you are close to a deadline, and the pressure is high, bonuses are at risk, and code that is not always top quality get committed. And this cannot happen in a project like Xen, where the maintainers are from Amazon, ARM, Citrix, AMD, SUSE, and more, because everyone works for different companies and they have different deadlines and different priorities. This is also very important for safety, and that's why I'm highlighting it. Now, this is an old slide, and I mean, with logos of companies working with Xen, I don't mean to go through it. I want to only bring your attention to the bottom left, because it's a part of the Xen community that not many people are aware of, and is also important for the safety background. So there are companies working in embedded, like the bottom right, in data center and cloud, top right and left. But there are also companies that work on security solutions. These are the bottom left. They're not maybe very well known. The CubeOS project is maybe the most famous. But there are several companies that are shipping product where Xen is the core, and their product is for security on laptops, desktop clients, or other devices. And security is another key part of safety. Not only it share many issues with safety, but there are also security certifications as well. Okay, so with this intro, I want to now focus specifically in embedded, right? Because many of you might have heard of Xen in the I don't know 2010 or 5, right? Very long time Xen has been used in the data center to run servers. So you might be surprised to know that is now a target for embedded. And that is because we had more than a decade to develop Xen for embedded, and we started in 2010, I think, with the Xen on ARM project that was made public, if my memory serves it right. But since then we did a lot, right? We changed many things to make Xen a better fit for embedded. I think at the core of it, there is a microkernel architecture, which is what allowed Xen to be a good fit. Meaning Xen remains small and is only running a small amount of code at the highest privilege level. But there are many other features that were added, and I think that make now Xen what it is today, which is I think is a great hypervisor for embedded. One of it is a small code size. Like I said, for ARM is less than 50K lines of code. DOM0, we're going to see it in a second, but it allows for parallel boot and remove a dependency for a Linux privileged environment. You can have it now, but it's optional. Real-time support with a number of schedulers, including Ring 653 and cache coloring for cache isolation. I'm going to go through quickly this feature one by one, just to give you an idea of the kind of configuration that Xen is using in embedded. This is an example that Philip Hamann and others are working as part of the ELISA systems WG. And if you're interested in knowing more, please reach out to Philip. And this is more maybe a typical industrial deployment where you have a critical environment based on Zephyr, which is real time, and a non-critical based on Linux, maybe Linux RT, connecting to the cloud, and Xen underneath doing the separation between the two environments, ensuring that Zephyr keeps its real-time properties and Linux can run well alongside it without affecting it. All right, so let me start from real time. So what Xen can do is it can split your physical CPUs into different CPU pools, and it can run different schedulers on different pools. So a CPU pool is a Xen concept. So you take a number of CPU, let's say CPU 0 and 1, they are one pool, and CPU 2 and 3, they are another pool. And then you can run the regular data center scheduler, which is actually credit 2 for in one pool, like we see at the bottom. And then you can also run no scheduler, which is what the null scheduler is. The null scheduler meaning there is no scheduling done. There is static assignment of virtual CPU to physical CPU, so one-to-one assignment, and that all obviously is the best for latency because there is no scheduling done. But you don't have to run credit. You can run something else. You can run, for instance, a ring 653, which is designed for real time. And so you can also have a real time scheduler. There is also RTDS available. Now, what about DOM zeroless? What is it exactly? So DOM zeroless is a way, first of all, the name is actually a bit misleading. In fact, we are trying to rename it to Hyper Launch, and that is work in progress. But DOM zeroless is a way to statically define all of your VMs and get them to start in parallel. Now, you might think of it like a parallel boot, but it's way more than that, as I'm gonna explain in a second. So on this slide, you see U-boot is loading into memory Xen, DOM0 kernel, DOM-use kernels, and then is booting them in parallel. I mean, U-boot boot Xen, and Xen is given some extra information about the domain to start, and then boot all of them in parallel on separate CPUs. So yes, it speeds up the boot, obviously, by a great amount. Like you could have something small like Zephyr in the yellow VM start in less than a second without even, trying very hard. But that's not the only, or maybe it's not even the main benefit. So it used to be that Xen would boot DOM0 first, and DOM0 typically is the Linux environment, large maybe, based on Debian or Ubuntu, potentially. And then you will have a number of Xen utilities in DOM0, and you will use those to create the other VMs. Now, what it means is you have now this dependency on this DOM0 environment that is fully privileged and is also pretty large. So it's not great for safety or security. Now, thanks to DOM zeroless, now the domain creation is done before before DOM0 is even created. And this is why the name DOM zeroless, right? Because DOM0 is not even in the picture when the yellow and the purple VM are created. They are DOM zeroless VMs. That's where the name comes from. But there is still a DOM0, and that's why the name is confusing. That's why we want to rename it. But the point is the domain creation is now done by Xen beforehand, and DOM0 is now optional. You could have a DOM0, you might not have a DOM0. You might have a DOM0 based on Linux, or you could easily have a DOM0 based on Zephyr. Because now that you move the domain creation out of DOM0, DOM0 is a pretty regular environment with a few extra hypercalls that it can make. So you could easily run something tiny like Zephyr in DOM0 or nothing at all and take DOM0 away. So that leads to far better configurations for safety and security. And it leads to configurations that are fully static. So you can statically define all of the VMs in your system, all the device assignment, the amount of memory in vCPUs, all in device tree before the system boots. You see some of the example in the at the bottom of the slide for configuration. There are tools to make it easier for you. One of which is called Image Builder, and you can write in a simple text file key property like how many VMs you want to have, which one are the kernel, and all of these device trees generated automatically for you. But the key point here is now you can define the system statically. You can even define the memory statically. Now you can, this is a feature that was added by ARM the company. And what we can do now, we can statically even choose the address ranges of each VMs. So we can say the first VM start from 3.0.0.0.0.0 to 5.0.0.0.0.0. And that would, the memory will be, statically allocated, which again is good for safety because it makes you're going to have a fully reproducible system. We can even define statically VM to VM communication channels. So we can define statically shared memory between VMs, and also event channels that are like software interrupts for notification between VMs. CPU pools. So like we talked about CPU pool a minute ago, and you can also define CPU pool statically as part of a DOM zero-less configuration. So as we saw, you can define the full system statically: CPU pool, scheduler, a number of VMs, VM to VM communication channels, static memory and address ranges. All of it can be done statically before the system boots. Okay, now moving on to another feature that I think is one of the most interesting things I had the chance to work on in the last few years, and that is cache coloring. So the issue is in many of our systems, and when I say our system, I mean SoC in general, there is an L2 cache that is shared across all the cores in the system. That is also true on the Xilinx UltraScale Plus, where we developed this feature. And what happens with a shared L2 cache is that it can be a vehicle for cache interference. So one core, by accessing some data, its own data, is causing a cache line eviction that then means that the other core will be slower to access memory. So much slower that in some cases it might affect real time. What if we could split the L2 cache in software and assign dedicated cache line to each core? That way there is no cache interference, and each VM gets its own set of cache lines that are completely separate and isolated from each other. And we can do that with cache coloring. It's a pretty sophisticated system, and the idea is you figure out how cache lines are allocated automatically to physical addresses, and then you as in the hypervisor smartly chooses physical address allocations to VMs in a way so that there is only its own set of cache line being used. So in practice, what it means is allocating one page every 16. Page 0, page 16, and so on to VM1, page 1, page 17, and so on to the second VM, page 3, and I think you got it. By doing this, you select one color for each, basically for each VM. And with this strategy, you can separate the cache lines and get extremely good latency results. And again, I'm not going to go through all of them in detail, but the point of this slide is there's a lot of numbers, but I'll tell you how to read the important numbers. So the one call and interfere are the one that are run with a lot of interference, especially the one with 3. There are 3 agents of interference causing problems in the system, and the impact on Xen without cache coloring is this high. This is as high as the light green box that is above 15,000 nanoseconds. So if you have cache coloring enabled, it's below 5 microseconds. So it's maybe 3, right? And it's very similar to the impact when there were only 2 interference guests, which is very similar to the impact when there was only 1 interference guest, which is similar to the impact of when there was no interference guest at all. So the point of this slide is to show that as you increase interference, latency goes up significantly when there is no cache coloring enabled. When you enable cache coloring, the latency remains stable and deterministic, which is exactly what you want in a real-time system. Okay, so if I've not convinced you up until now that Xen is an embedded hypervisor, I think this slide, which is the last slide on my intro on Xen, before I switch to safety, this slide should really convince you. So, as you might know, I don't know if you are that familiar with hardware details, but in all the system where a hypervisor typically runs, and all the system where Linux typically runs, there is an MMU. So the MMU is the unit that converts virtual addresses into physical addresses. And when there is a hypervisor, typically there is an MMU that is capable of doing even 2 levels of translation. That is not shown in this picture here, but it can do from virtual to guess physical and to guess physical to physical. Anyway, so all your system, x86 systems, ARM systems, RISC-V systems, you name it, have an MMU. There are some systems that are truly embedded and maybe more for microcontrollers rather than full operating systems, where there is an MPU instead. What is an MPU? An MPU is a memory protection unit. And what it does no translation. There is no translation between virtual to physical. There are some address ranges that are protected, and that's it. So Xen has gained the ability to run on MPU systems. So now Xen can work on both Cortex R52 and R82, which are MPU systems only. So there is no memory allocations. So no memory allocation, sorry, no dynamic memory, right? Because with an MPU, you can't really have easily dynamic memory due to the fact that there is no MMU. And this is a place where typically on an R52, Linux does not run. I'm going to explain why it can run on an R82 in a second. But on an R82, you can run Xen, you can run Zephyr, and today you couldn't run Linux because Linux requires an MMU. So you can use Xen to partition your system, to run multiple Zephyr guests, as an example. On an R82 instead, because the R82 is, first of all, has 2 key differences. One is a 64-bit system, and second, it can support MMU system as guest only, not as hypervisor. So you could run Xen on an R82 and run both Linux and Zephyr as guest on an R82. All of it is available and publicly available, not yet upstream, but the upstreaming is in progress. We are working right now, some of the foundation to get the MPU supporting Xen for this release. Okay, so now I'm gonna talk to you about maybe the real reason why you're here, which is safety and Xen. And I'm gonna give you details on where we are with this project, but also I'm gonna try to provide lesson learned that can be applied to other open source projects as well. So let me start by saying that Xen is the reference open source hypervisor for embedded and automotive at AMD. And that is for both the ARM and AMD x86 architectures. And we have a team to improve and enhance Xen for embedded in the company. And Xen is given to customers and supported by us through forum and technical support and engineering. And also, I'm going to highlight this because it's also important for safety, but we do have customers in production using Xen for hard real-time isolation between VMs. Now, these are some of the characteristics of the Xen as a project and Xen as a community that make Xen a good candidate for a safety certification or for safety certifiability. First of all, Xen has an extremely strong quality and validation process already in place. And in particular, Xen has a very rigorous review process and is famous industry-wide for being hard. Like it's traditionally very hard to get patches in Xen, and the review is extremely strict. And we get complaints sometimes that is by new contributor that is too hard. And Now, the flip coin is that if you want to run a software in an environment where human lives are at risk, you do want the review process to be hard and even too hard, right? So this is good for safety and security. We also have a very strong security process to handle security vulnerabilities with responsible disclosure. It's very detailed and has been used as the model for many other open source community and projects. Security and isolation have been top priority for Xen for many years, at least from, like I was saying, maybe 2009 or 10, when projects like QoS, OpenXT, or their predecessors at that time, like Xen Client, started, that were all about security. We have full traceability of commits because all of the communication is done in public on XenDevel, and the archive goes back to 20 years. So this is similar for Linux with the LKML. We do have commits that are tested not by one, but by two CI loops before entering the master branch, one of which is based on real hardware only, and the other one is Gitlab-CI, which is based on QEMU mostly, but also real hardware. We do also have a strong history of Xen being used in critical production environment, maybe not safety environment, but still critical production environments where isolation is important, such as Amazon AWS or Rackspace on the data center, or QoS, like I said, in the desktop, or Xilinx Petalinux in embedded. So AMD is working on making Xen safety certifiable for AMD platforms, and that is both the ARM and AMD x86. We are targeting IE61508 Seal 3, as well as ISO 26262 ASIL-D. Now, these two certifications are comparable to DO-178C between DAL-B and maybe DAL-C in aerospace. This certification is based on Xen upstream community processes and upstream community efforts and code base and releases. Now, this is very important because you see, like, open source software has been certified many times in the past, and Xen is one of them. But the way it was done before is someone took a snapshot of the project, like Xen, and then started making changes, and what basically inherited this software from the open source, but then continued the development and the certification inside their company and certified their processes within the company and their own workflow and changes on top. That is not what is happening here, right? What we are doing is working on the safety certifiability of upstream Xen releases and Xen community development processes, not a private fork. Now, these are two great benefits. Like, one is gonna directly benefit the community with our work and the artifacts that we produce, but also is gonna make us being able to rebase way more easily the artifacts in the future. So the intention is to be able to move and keep the certifiability artifacts up to date with newer Xen releases. So there are a number of things that needs to be produced in terms of documentation, requirement testing, and more. Many of them are going to be open source, and I'm going to touch on some of them during this presentation, but not all of them. And some of them will be only available for AMD customers. But some of them that are going to be open source, and we have already started working on them, are MISRA C compliance. In collaboration with Bagsang, we have already made significant MISRA C improvements in Xen. Public interfaces documentation, as well as other type of documentation in the project, and testing. And I'm going to talk more about all of these three in details. So what is the scope and the assumptions made? So again, we're targeting both ARM and AMD x86, only in the newest hardware. So we assume virtualization extension in hardware, on both architectures. We assume an IOMMU present on both architecture, a timer with virtualization extension on ARM, PCI available, and other things like that, which are basically available on all the recent SoCs. Xen is easy to port to future generation of hardware because Xen does not have that many drivers. Pretty much only the drivers for the components that you see on the slide. We are also going to include VM-to-VM communication and the building block for PV drivers, and I'm going to touch on them in a second in the next slides. But these are components that allow you to share memory either statically or dynamically between VMs and send VMs to VMs notification like event channels. They are like software interrupts. So there is no OS hypervisor dependency. You can run any safe OS or any non-safe OS that you want. You can run Zephyr, you can run more than one Zephyr, all of them safe. You can run Linux, more than one Linux as QM, meaning non-safe OS, as you wish. You can mix and match in any way that you like. There is no tie in the number of safe OSs or the number of non-safe OSs or the OS running inside. We are assuming DOM0less or hyperlaunch, as we are trying to rename it, on both ARM and x86 for domain creation. We are going to restrict DOM0 privileges so that there's not going to be a fully privileged, all-powerful DOM0. On x86, there are more than one type of VM, and we're only going to use the latest, which is PVH, and is comparable to the ARM type of VMs, meaning is using the latest hardware, which is great, but at the same time does not need any emulation. So there is no QEMU or no VMM in KVM terminology needed. It's a fully static configuration, and we are going to support real time, of course. We are assuming that most devices are directly assigned, but we can also support VM-to-VM communication in terms of static share memory, as well as device sharing with VirtIO and PV drivers. And in case of device sharing, we can share a device with safe OSs as well as non-safe OSs, which is something that is non-common. And I'm gonna give more details in a second. So VM-to-VM communication is what I mentioned in the past. Is basically a simple static share memory plus a notification mechanism, and you can build anything that you want on top. Now, this is very simple, but it gives you the ability to define the communication protocol that you want. So sometimes people want to have a full control over the way the bytes get across, and that gives you the way to do it. But some other time you just want to share a device, like the network or GPIO between multiple VMs. And we're going to support both PV drivers and VirtIO, as I said. Both work the same way architecturally, like there is a backend and a frontend. The backend is basically a proxy. So the way it works with Xen is you have a GPIO driver in this case, and you can assign it anywhere you like. Like, for example, by default, it gets assigned to DOM0, but you can assign it anywhere you like. Let's say you have it in DOM0. You run the GPIO driver in DOM0, and then you also run the backend in DOM0. The backend is this proxy that mediates access. Then the other VMs run frontends that connect to the backend to get access to the to GPIO. Now, one option is to assign the GPIO to the safe OS, run the GPIO driver in the safe OS and the backend in the safe OS. Now, this is good because it gives you in the safe OS full control over the GPIO. But it means there is more code than you need in your safe OS. You need the GPIO driver, you need the backend, which is a proxy in the safe OS, all of it to be potentially safety certified. That might be okay for GPIO, but might not be good for other much larger devices, such as a GPU. So let's say that you have a GPU and you want to use it. The GPU might have alone millions of lines of code. So do you really want to put the GPU driver in the safe OS? The GPU driver alone will be 20 times the size of Zephyr, maybe more than 20 times. So it would take a considerable effort to port the driver to Zephyr, and the end result very likely will not be as stable, as safe as running it in Linux, because the GPU has been running Linux already for hours and hours, millions of hours of production usage on Linux laptops, Linux desktops, and Linux servers. So what Xen allows you to do is to take the GPU, you assign it to your Linux QM VM, like non-safe VM, you run the GPU driver in Linux, you run the proxy in Linux, which is, these are their native environments. You know, they're going to run better there than in other environments, because that's where they have been tested. They might not be safety certified, but that's where they have been tested and run. And then you connect to the backend from the safe OS. Now, this takes extra caution, because if the Linux environment crashes or becomes unavailable, Zephyr that needs to be unaffected, right? And so there needs a number of precautions you need to take. But this environment, what I'm showing to you in the picture, if you have something as large as a GPU with a GPU driver, might be the best choice. And this is also something that Xen allows. So Xen does not really have an opinion to where you assign your device, whether it's the safe OS or the non-safe OS, where you run your driver and backend, and who connects to it. It could be that you're assigning it to DOM0, and DOM0 is your safe OS. You can assign it to a DOM-U, and DOM-U is the non-safe OS. You can do anything that you like. And in this example, I mean, this is just to pull everything together. You have an example with a DOM0 with Linux. Maybe has been restricted in its capabilities, so it's not an all-powerful DOM0 anymore. But then you have a DOM-U that is Linux, and there's a yellow VM with device driver for GPU and audio, and the PV backends for those. And then you have Zephyr as a safe OS, that's a green VM, with a few more devices as directly assigned, like the CAN bus and GPIO. But you also have PV frontends connecting to the backend in the yellow VM. And you might have an extra VM like Android also connecting to the yellow VM. And this is just an example, because you could have in this picture more than one Android and more than one Zephyr. So it's all depending on how you set up the system. Okay, now to go more in details about safety certifications. So the plan is divided in two phases. The first phase is safety concept review, which this is where we are now. The second phase is the final assessment. And the first phase has a number of deliverables, but is mostly plans, as you can see in these slides, like the safety assessment plan, the safety plan, the requirement management plan, other plans like that, to give to the assessors so that they can see that we are heading down the right path, and they can give us a safety concept approval letter, which is a letter that says, if you do what your plans are saying that you do, then you are going to get to a certification at the end. The second phase is where the actual, the key deliverables are provided, including the FMEA report, the MISRA C compliance report, all the requirements, all the tests, the traceability reports, and more. So instead of going through the details in that slide, but if you have worked with safety before, you have likely already recognized those names of the deliverables that I showed. But if you're not worked on safety before, I wanted to just give you a taste of what this means in practice. What this means in practice is we need requirements for everything. And what the requirements are is basically a description of all the behaviors of the software. So how can you make sure that your software is safe if you have not documented what your software is supposed to do? So the requirements are there to describe in every circumstance what the hypervisor is supposed to do, both errors, non-error, normal behavior, etc. Then obviously all the interfaces need to be documented. MISRA C is a safe C coding standard, and that needs to be followed. And then tests. like all of these requirements need to be properly tested to be and validated to make sure that your behavior is consistent with with actually what it should be. What this means is, this is a rough estimate, but the effort is roughly 65% testing, 35% documentation. And in our experience, a code size of roughly 50K lines of code will take between 2 years and 2 years and a half to reach safety certifiability. Like I said earlier, we want to keep this close to the upstream community to make sure we can upgrade the safety artifacts at the when appropriate, when in future releases. But I want to spend the last few minutes to talk about the impact on the Xen community. Like we talked about what the process is, we talked about what is Xen for embedded. What is the impact of safety certifiability on the open source project? So there are a number of things to consider. I think the impact is very positive. So first of all, this enables Xen to enter many environments where Xen couldn't even be considered before, such as safety critical industrial use cases, safety critical medical use cases, safety critical vehicles on the road, trains, and of course avionics. But in addition to, and more user, of course, means also more developers, and that's better for the community. But there is also a more direct benefit to the community. So even just the proof that Xen has been made safety certifiable paves the way for many others to do the same for different verticals, for different safety certification. Makes it far easier to do. And there is also a concrete positive impact on the community today. And I'm going to talk about it starting from MISRA. So MISRA is a set of coding guidelines to turn C programming into a safe and secure programming language. And the adoption of MISRA C is now maybe the most important things for safety, but is one of the most impactful for the open source community because it touches the code itself. And maintainers and the community is mostly about the code. More than anything else, what really an open source community usually is about the code. So MISRA C touches the most important part, and this is why it's usually the topics that is discussed the most. So the way we did it is, first of all, we evaluated MISRA C together with the community, and we explained that we are doing MISRA C for the benefit of the open source project, to make the code actually safer, to improve the code quality of Xen. And then together, and well, I should add one thing, and also to use automatic code checkers to scan the code. Like one of the things about MISRA C is it comes with very powerful, thorough code checkers that can scan the code base for MISRA C violations. And basically, they catch a lot of those issues, and normally they're caught during review. So they make the review of maintainers easier, and definitely is one of the goals here. So together with the community, we looked at the MISRA C rules, and we found about 143 rules that are relevant for Xen. This process is called tailoring, and then one by one, we started evaluating them for adoption. Together with Roberto Bagnara, that I think is in the call, and he helped greatly to explain the rules, exactly how they work, and we adopted them one by one as part of the Xen coding style. Now, once the rules are added to the Xen coding style, then anyone in the community, any new contributor, anyone can send patches to fix violations. And in 2023 alone, we have 125 commits to fix MISRA C violations, and most of them are from Bagsang. We also have introduced an open source deviation strategy to allow us to introduce deviations without being tied to a specific tool. What is a deviation? A deviation is is when you have a violation of a MISRA C rule, but you think it's safe, and it's safer to keep it as is than to change the code to be MISRA C compliant. So that's what a deviation is, and you need to mark a deviation as such so that the MISRA C scanner does not catch it as a violation every time. So we have a system to have in-code comments like the one you see on the box at the bottom of the slide, and they can be converted with a set of scripts to specific tool-specific deviation tags, such as CPP check deviation tags or eclair deviation tags. One thing that we did that also helped a lot is AMD sponsored an MISRA C training course that was done by Xen for all the maintainers and the key members of the community, and that greatly helped with the understanding of MISRA C and the adoption of the rules. MISRA C is not the only thing that we are doing, so we are also writing documentation for all the key interfaces of Xen, both user-exposed interfaces and also other interfaces such as hypercalls. And the maintainers, of course, are going to keep them, are going to require to keep the documentation up to date in the future when the interface change. The documentation is kept as RST files under Xen.git to be close to the code and kept in sync with the code. And testing. So we are greatly enhancing Gitlab-CI, with many tests. Most of them are based on QEMU, but now we even have real hardware runners, so you can run Xen on bare metal hardware, both ARM and x86. One of the hardware runners is sponsored by AMD, and the other one, I think two others, are sponsored by Cubes. In this test, we test a number of things, including DOM zero-less, DOM zero-based configuration, ARM and x86, and more. And we are doing more with Gitlab-CI. At the beginning of the next development cycle, we'll adopt Gitlab-CI as making it gating. So a failure in Gitlab-CI will actually block a commit for entering the master branch. One of the things that we did also is we integrated MISRA C scanners as part of the Gitlab-CI, which means that the first step of the Gitlab-CI pipeline is to run CPP check and eclair on the code base to find violations. And at the moment, these scans are non-blocking, meaning they're not going to stop the pipeline. But the intention is soon to turn them to actually block the pipeline if new violations are found on the MISRA C violation I'm talking about. New MISRA C violations are found on the code base. One word on eclair. So eclair is a MISRA C scanner by Xen, which is itself safety certified and is extremely thorough and precise as in the level of MISRA C scanning that it can perform. Okay, there are a few more details on Gitlab-CI, but you see some of the build and test jobs here in the picture. As I said, we have build jobs, test job based on both QEMU and real hardware. This is some of the details on the jobs that you see. We have ARM64 hardware runner based on Xilinx, AMD Xilinx hardware, and CubeOS hardware runner based on both AMD x86 and Intel x86 hardware, and many tests based on QEMU. Yeah, I'm going to skip this slide and reach the conclusion, saying that Xen is an open source project under the Linux Foundation with a healthy and diverse community. It's a real community project. We support many embedded features in Xen today, such as DOM zero-less and cache coloring and real-time and more. Isolation, security have been top priority for Xen for a number of years. AMD is working today to make Xen safety certifiable for AMD platforms. And we are doing most of this work upstream together with the community. And many of the lessons, I think, many of the details I showed here, they can be applicable to other open source projects too, such as an example, is security or code quality top priority for your open source project? Now, if so, and if your open source project is in Brittany C, then MISRA C can be a very strong candidate for adoption, because MISRA C does improve your code quality if adopted correctly. Is your community willing to prioritize testing over new features? Now, writing tests costs more time and effort than writing 0 tests. And of course, if you write 0 tests, you might spend your time writing more features. So what are the priority of your community? If your community has as a priority top quality for the code base, and they're willing to prioritize tests, MISRA C, documentation, things that make your code, your projects higher quality over adding more and more new features, then I think your open source project could be safety certified too, right? And for the benefit of the community, right? MISRA C will make certain classes of error either impossible or harder to introduce. And more documentation will make your interfaces easier to maintain, easier to use from the users. And testing, of course, is going to validate release by release all of the key features and configurations that you support are still working, rather than relying on ad hoc manual tests that are sporadic and sometimes easily forgotten. And with that, I think I'm at the end, and I want to leave a few minutes for questions. So I'm going to open the floor to Steve and anyone else that might have questions for me.
Stefano, thank you very much. This is great detail, wonderful presentation. We do have 5 minutes to do questions. Are you able to see the chat, Stefano, so you can read through them yourself, or do you want me to read them to you?
Give me a second.
And for the audience, if you'd like to express your appreciation, there is a reaction button, and you can click the thumbs up or the clap to show appreciation for the presentation.
So I know other translation, I guess the comments refers to the MPU. So the other translation is, of course, there when an MMU is used. When an MPU is used, there is no other translation at the hypervisor level. Any particular reason you want to use the L2 cache? Because it can be disabled. No, if you can disable the L2 cache, this is great. I think there are multiple reasons to enable the L2 cache. One reason is it can be a lot faster, right? So if you can run a small bare metal or RTOS environment entirely from L2 cache, which is what typically we do, then is a lot faster than turning it off. That's one reason, is performance. Second reason, certain software such as Linux might not work that well if you disable the cache. In fact, I believe they will not work at all. Yeah, so these are the two reasons to keep the caches enabled. If you only have a small real-time OSs, then you could disable it. Any reason why the MPU support cannot be backported to Cortex R5? Yes, the reason is on R52 and R82, there is an hypervisor mode. So Xen is taking over hypervisor mode, also called EL2, and is running at EL2. On Cortex R5, there is no EL2. So there is no extra privilege mode where you can run Xen. That will make things harder. So it's not as easy as you can port it to the R5, unfortunately. Again, about caches and real-time system. So if you have a system where you can disable caches because you don't have a large OS and all of your OSs are fine with caches disabled, this is a great solution, and you can do it. Right? You can just go and disable the cache. It's a one-line change in the Xen code base, and for sure that is totally okay. Let's say which level determinism you can achieve with device sharing. No, that definitely can be a cause of interference. So the more sharing you do, of course, the more interference there can be. Now, device sharing is tricky because Xen is not in the middle of it, right? It's all up to the way you write the front end and the way you write the back end. So improving Xen will not improve your device sharing experience. So the device sharing interference depend on how you wrote the front end. And now when you say wrote, I mean, you mean which front end you adopted or wrote yourself and which back end you adopted or wrote yourself. And if you write the front end very carefully, you might be able to write a front end that is free from interference. But it's up to the way you write the front end. And if the front end simply blindly waits for interrupts from the back end, maybe busy waits for interrupts or does things that are obviously not good for interference, then of course you're not going to have a good solution there. On the other hand, if you have a front end that is very careful with the data it accesses from the back end, access data from the back end very carefully, does not trust the response time from the backend, then you can still have an RTOS with a shared device. Of course, the shared device access will not be real time, right? But at least the rest can be real time. But it's all in the between your front end and your backend, and Xen is not in the middle of it. And this is why, if you need real time on a device shared, I think you might want to instead write your own VM-to-VM communication protocol, which is a lot simpler and a lot easier to make sure real time is preserved. Xen does support VTD and the equivalent on AMD, and VTD is Intel terminology for and it does support the equivalent on AMD and ARM. We do have both open source tools to scan for MISRA C and proprietary tools. So Eclair is an example of a proprietary tool scanning for MISRA C, but we are also using CPP check, which is a fully open source tool to scan for MISRA C violations. So CPP check is great because you can install it on any of your laptops, including mine on Debian. You can run it. However, it's very rudimental compared to Eclair. So and this is also one of the reasons why we are using both as part of our CI loop and our community. The safety plan. So some of the work item for phase one of the safety assessment, are they available? For example, the safety plan. So they're not available today because we are still working on them. The safety plan specifically is one of the document that we do not today think of releasing publicly. Does then make any assumption on the behavior of U-boot or any other bootloader in order to run safely? Is there a recommendation strategy to prevent the contamination of the certification of U-boot? So we don't have that many assumptions because I mean, in the DOM zero-less boot that I showed earlier, there is no dependency at runtime on the bootloader. What I mean is there is nothing that survives booting Xen of the bootloader. Now I'm saying this because, as you might know, with EFI, there are certain things like EFI runtime services that keeps running. Now, of course, Xen can boot from EFI, but it can also boot without EFI from U-boot. And if you boot without EFI, as an example, you have no runtime dependency. On the behavior of the bootloader, of course, we rely on the bootloader to load the binaries, as well as passing the information to Xen to know how many VMs are to be created. So I do think there is full separation between Xen and U-boot, and the contamination is not easy, at least unless you use something more complex, such as EFI runtime services or ACPI. With both of them, we do not plan on using. Well, thank you for people that like the presentation. And if you have any other question, feel free to ask them or reach out to me on by email or any other ways, and I will be very glad to answer your questions.
Thank you, Stefano. And if any of you in the audience have colleagues that would have been interested in this presentation, it has been recorded. Once that recording is available, we'll make sure it's posted in the Aerospace Working Group minutes and maybe on the ELISA homepage as well. Again, thank you, Stefano. Great presentation, great questions. Thank you, everyone, and have a good day.
You too. Bye.
Thanks.